Okay. William, are you there? Mhm. Okay. Well, this is one of the propositions. It's actually our proposition 20, XX 20. Basically saying that if two angles are equivalent, then the the side opposite to the angle, which so this side is opposite to this angle, then and this side is opposite to this angle. So the two sides opposite to the angles are congruent. So therefore, by definition, that this is isosceles triangle. But how do we prove that? Okay, so when we do proving in geometry, we're always using we call 8 lines. So something to help us, and we're actually going to construct the 8 line. And also remember, in Euclidean geometry, we only have the straight edge and the compass as our tool. But we know this. Let's say this angle is A, B, C. So we know that we can draw the line to bisect the angle C. So we know that. This is one of the proposition is that we can draw, um, we can construct a line to bisect an angle. So now, and this one uh, intersect with the base at D. So now what we know is we know angle A. Okay, let me uh, do that more formal. So we're going to have, we have statement, we have reasons. So, so the first thing is we're going to construct CD, which bisect angle C. And we know we can do that. So one of the proposition has that. So the next one we are going to do is we know A is equal congruent to angle B. And that's just given. That's given in our proposition. It's given because we said that if in a triangle the two angles are congruent, then the opposite sides are congruent. So therefore, it's isosceles triangle. It's a given. And we also know CD is congruent to CD itself. So it's just itself, of course. Anything itself will is equal to itself. And now, because of that, and we know ACD. ACD is this angle. ACD is congruent to BCD. So that's because we did bisect. We know the CD bisects angle C. So therefore, this side will be congruent to that side. And now, because that's the case, we know uh, A is congruent to angle B, and ACD is congruent to BCD. So therefore, we know this has to be true. ADC C is congruent to BDC. So why is that? Why is that the case? So we know angle A is this one here, is congruent to angle B. And we know ACD, which is this angle, is congruent to B, BCD, which is this angle. And we said that this angle has to be congruent. And they have actually also has to be a right triangle, a right angle. Okay. Hello? So why is that? Why do we say ADC is congruent to BDC? And they're also right triangle, right angle. Is this angle ADC? ADC is this angle, and B BDC is this angle. Okay, while saying that these two angles are congruent, and they are
I said,
both.
I think so. I think they're congruent.
Hello?
Hi, so can I, so like, I think that angle ADC is congruent to BDC because, so, first of all, there are two angles that are the same between them.
All right.
And there's also one side that's congruent. So that means that the whole triangle itself is congruent. So then the angle has to be congruent.
Okay. Uh, Actually, you don't have to go that far. Is remember in a triangle, the sum of all the angles is what? So in a triangle, the sum of all angles is 180, which is we call straight angle. So in Euclidean geometry, we actually don't have the angle measurement. We can just say that it's either a right angle or straight angle. So we know that. Uh, so we know this at this angle A plus angle ADC plus angle ACD is a straight angle. Straight angle. I think it's just like that. So therefore, since we have this and that equal congruent, and this congruent, then this has to be congruent. And also because they are in uh, a line, so the sum of these two triangles are straight angle. So then each one of them has to be right angle. Good? Okay. All right. So now then we can see, okay, because we know we know this by itself is congruent solve, then we know this angle and congruent to that angle, and this angle congruent to that angle. So we know um, the triangle ADC is equal to triangle congruent to triangle uh, BDC. So on this one, what is the what's the proposition we use to say it's congruent? Remember when we say congruent triangle, we got angle, side, angle, and we have side, angle, side. and also have side, side, side. So in this case, um, we know angle ACD is congruent to angle BCD. That's angle equivalent. We know CD is congruent to CD is by itself. Now we know ADC is congruent to BDC. So therefore, we know this triangle is congruent. So because this triangle is congruent, therefore we know AC is equal to congruent to BC. So it means this line is congruent to that line, and therefore it's a isosceles triangle. Good. So let's just kind of quick review on this one. Quick review on this one is if there is a triangle and if we know two angles are congruent, so we got A, B, C. So if A is congruent to B, well, that's all we need to know. If this is congruent to that, then we know AC is congruent to BC, and and also angle uh, ABC is a isosceles triangle. Okay, we have that. And now we're going to have another um, something based on this. Yeah, I have problem actually um, pronounce this word. Mm, okay, so in geometry, we have axioms that we do not need to prove, and also uh, postulate we don't need to prove. Then we have proposition. So proposition we have to prove propositions. Then we have something is called let me see. Let me check on this word. Okay. Okay. It's called corollary. Let me show you. It's corollary. Okay. The corollary is basically a logic extension from the partial proposition. So I have proposition, then we get corollary. Corollary is just extension of that. So now we see example of that. The example of corollary is that um, if a triangle is they call equal angular, equal angular. So that's big word, equal angular. So that means all the angles are equal. This and that and that. And the corollary is, if that's the case, if we have if ABC, angle ABC is equiangular, then uh, it is also equilateral. So which means if we have ABC, the angle ABC, all the angles are the same, congruent, then that's all the sides will be congruent. Okay. And the reason we say this is a corollary is because remember our proposition said if we have two angles are congruent, then their opposite side, this and that, has to be congruent, which means it's isosceles triangle. But we can also looking at the other angle. We know this angle, me different color. We also know this angle and that angle is congruent. So therefore this side is also congruent to this side. So that means all sides are congruent. That which is a definition of equilateral. So this is the reason we call this is a corollary is because we can use the proposition we have proved, and then just that's the logic uh, extension of that proposition. So are we good on this one? All right. Okay. Hmm. I think that's what we're going to have for today. Okay. Yeah. And so from now on, I'll start to have you do some proving, okay? So that you can get used to this uh, kind of math. So yeah, this is kind of different from what you're used to. It's different from algebra. Like algebra, we just play with symbols, and but for Euclidean geometry, uh, we actually play with the shapes. And in Euclidean geometry, we actually don't have a measurement because our tool is a straight edge, which has no marker, so we cannot use to measure. And also the compass. Compass cannot we cannot use to measure either. And so in Euclidean geometry, we really just talking about if some a shape is congruent to another shape, or is maybe the angle is less than the other angle, or is great one angle is greater than the other angle, but we just don't know how many degrees there are. And this is what Euclidean geometry is. But nowadays, when you learn geometry in school, they actually mixed uh, Euclidean geometry with algebra. And so, I mean, in a way, it's it allows us to do more things, but in uh, in the other way, that it's can easily confuse student, and also um, you won't be able to learn how actually to prove something, how based on something we know, and using that knowledge to prove something we don't know. Okay, so that's what we have for today. Okay, I'll see you next time.